Welcome back everyone to another video. Today we're going to be going back to consider the derivative of sine x because the way I did it in my first video was very complicated, but there was a reason for that. And I want to show you the more standard way of showing it using the difference quotient that confuses a lot of people. At this point, we're very well accustomed to the difference quotient and we know what it's going to look like for sine. The limit as h approaches 0 of sine of x plus h minus sine x all over h. So now we can use the sum of angle identity for sine to split up this x plus h. So we know the sum angle identity is like this. Sine of, we're just going to use x and h here, x plus h is equal to sine of x times cosine h plus sine of h times cosine x. All right? We sub that into our limit. We have sine x cosine h plus sine h cosine x minus sine x all over h. Now what you get when you factor out a sine x from here and from here is sine x times, you take it out of the limit because there's no h's associated with that. You have the cosine h minus just 1 and then over h. And then what you're left with is this bit where you can take out the cosine x because it doesn't have an h outside the limit and you get this limit. The limit as h approaches 0 of sine h over h. This limit is iconic because there's a very nice trick you can do with limits like this where if you just plug in the number, when it evaluates to 0 over 0 or infinity over infinity, you apply what's called L'Hopital's rule. You differentiate the top and the bottom, and then you evaluate the limit with that, and it works, and it's great, except if you try to differentiate the top, you need to find the derivative of sine, but we're trying to prove the derivative of sine. So it's circular reasoning, and it's no good. You can't use that trick. So there's a geometric proof that you have to use to verify, and it's kind of hard to explain, and I won't get into it in this video, but you can look it up on your own if you're interested. This is Editor Ben. I was very wrong. We do very much end up going into it. What I'm going to be doing is, instead of looking at the limits, the confusing thing for sine, we're going to be dealing with cosine. So we put it in our different quotient form, and now we're just going to apply the sum of angle identities for cosine. So that identity is going to be cosine of x plus h is cosine x cosine h minus sine x sine h. Now we substitute that in, and this is the expression that we get. So now let's do some factoring, and as a result, we find these two limits. Cosine x times the limit as h approaches 0 of, wait a minute, this looks basically exactly the same to the limits that we had before, so how could this possibly be better? Aren't we just having the same confusing things that we were dealing with before? Well, here's where the choice of using cosine x for the derivative ties in. You see, the graph of cosine x looks like this. Now, at x equals 0, we see that the slope of the tangent line, the graph there is at a maximum. So the derivative must be equal to 0 because the slope is 0. And that tells us two things. One, cosine of 0 is equal to 1. And two, that the derivative of cosine at 0 must be equal to 0. Now, what we can actually do is show this here. Since this expression on the bottom represents the derivative of cosine x at any value of x, we can just use x equals 0, which we just showed is also equal to 0, right? Cosine prime of 0 is 0. Then that means that this expression must be equal to 0. Now what do we notice? Sine of 0 is just 0. So this actually cancels out, and we're left with that this expression is equal to 0. But wait a second, cosine of 0 is also just 1. Therefore, this limit of cosine h minus 1 over h as h approaches 0 must equal 0. Recall the expression that we found earlier for the derivative of sine x. We had this expression, sine x times this limit plus cosine x times this limit. Except this one's 0. That's very nice. Okay, we're halfway there. We now have that the derivative of sine x is cosine x times this very special limit. Now, how the heck are we going to evaluate this? Well, there's a lot of very tricky and clever geometry here, so let's get into the proof of what this limit actually is. We're going to create a geometrical construct on the unit circle. What we see here, there's a lot going on, but we have our standard 1 sine theta cosine theta with angle theta. We understand this, we know this is all good. But then if we extend this triangle so that the bottom side is the whole radius of the circle, it becomes 1. Now what that means is that since this is a right angle, this is a right angle, and this is the same angle, these two angles must be the same, and so they're similar triangles. What that means is that there must be some sort of scaling factor for the two triangles. And we see that to get from cosine theta to 1, you need to multiply by 1 over cosine theta or by secant theta. So of course 1 times secant theta becomes secant theta, and then sine times secant is sine over cosine, which is tangent. And so we get this 1 tangent secant triangle by extending the triangle out. Now in between, we have the arc length of the circle, where arc length is equal to theta r. Since the radius is just 1, then the arc length is equal to the angle theta. Now we can see very clearly here that for this acute angle, right, less than 90 degrees, theta must be less than or equal to tangent theta and greater than or equal to sine theta. So now we have this value, and we're going to want to take a limit after reworking some of the algebra. So here's what that's going to look like. We start with this inequality. We begin by dividing all of them by sine theta, and since we're dealing with positive angles, sine theta is going to be positive in this case, so we don't have to change the direction of the signs. Sine theta over sine theta is just 1. Then we have theta over sine theta, and then tangent theta over sine theta. Tangent is sine over cosine, so it cancels out the sine on the numerator, and it leaves us with just 1 over cosine. Next, what we're going to do is we're going to flip all of these. 1 over 1 is still just 1. 1 over theta over sine theta is going to be sine theta over theta, and then flipping this 1 over cosine, we just get cosine. And of course, when you do this, now you do have to worry about the order of the signs as they're going to flip. Now we want to take the limit as theta approaches 0 from the positive direction, which is what we were doing with that example. We want this angle, theta, to get as small as possible to show how that limit works. When we do that, we find that the limit as theta approaches 0 of 1 is just going to be 1. It's just a number. It's just 1. But for cosine, the limit as theta approaches 0 for cosine is going to be 1. So we see that the limit as theta approaches 0 from the positive direction of sine theta over theta is either it's less than or equal to 1, and it's greater than or equal to 1. But the only way to satisfy both of those conditions by the squeeze theorem is that the limit must be exactly equal to 1. Now, technically, we haven't solved it yet because we need the limit overall, not just the limit as theta approaches 0 from the positive side. Here's the process that we can use to solve this problem. Consider the definition of an even function. A function is even if f of x is equal to f of negative x. If f of theta is equal to sine theta over theta, then f of negative theta is equal to sine of negative theta over negative theta. But sine of negative theta is equal to negative sine of theta, so we can bring this negative out. These two negatives will cancel, and we get sine of theta over theta, which is the positive version, so we've shown that f of theta is even. Now, for any even function, the limit as x or theta or whatever, the input approaches 0 from the positive direction, is going to be equal to the limit as it approaches 0 from the negative direction. In other words, the limit as it approaches 0 is going to exist, and in this case, we showed that the limit as theta approached 0 from the positive direction is 1. That's equal to the limit as theta approaches 0 from the negative direction, and therefore the limit as theta approaches 0 of sine theta over theta is equal to 1. Now we're almost done. The derivative of sine x, as we saw earlier, was cosine x times that limit. But since that limit is 1, we can say that it's just equal to cosine x. And so we've found that the derivative of sine x is equal to cosine x. I hope you're able to follow the geometric proof. Let me know if you liked it more than my explanation, my methods, down in the comments below. And thank you so much for watching.